Hey, this is a small video on surface integrals, like what they are, what do they look like, what do we get from them, and how to evaluate them in Matlab. So surface integrals are basically finding the surface area, and surface area is just the area which defines the boundary of an object or a function or a 3D thing. So the basic definition of surface integrals is given here. S is equal to double integral ds, where ds is your small component of the surface and r is your region. Ds is given by this formula, which is under root 1 plus del g by del x the whole square plus del g by del y the whole square, where z is equal to g, x comma y is the function of your object in 3D. A good way to see this formula is via the rectification of curve, where you have a function y is equal to f of x and you have to find the arc length of the function. So you have ds here, where ds is your small element of the arc length, which is given by ds square is equal to dy square plus dx square, and by a small manipulation you get the formula ds is equal to under root 1 plus dy by dx the whole square into dx. So if you integrate the whole thing, you get total arc length. So similarly in surface area, we have this function z is equal to g of x comma y, and we have similar formula as we had in rectification of curve. So we can see that this dA is basically the projection of this element on the xy plane, and this thing here gives the little bit elevation to that area, which eventually converts a projected area on xy to a surface area. So that's the basic idea behind this elemental area. So let us see what surface area looks like in 3D. So this is your function in 3D, 3D object, and if you remove all the integral part, you are left with the surface area. So this is what surface area looks like. So there is a small code in Matlab to evaluate surface integrals. The code is similar to that one in double integration. So the first thing in the code is you input the function of z is equal to g x comma y, and second thing is you take the partial of g with respect to x and y respectively, and then you convert the whole thing in the standard formula of f is equal to square root of 1 plus del g by del x the whole square plus del g by del y the whole square, and then you define the region. So the region here, I have added one more region which I had forgotten to add in the double integration one, where your region is defined by two different curves and two different limits. So the curves are but obviously not intersecting each other at two different points, but they are defined by two different limits. So first one is the rectangular one, which is simple one. You just need to know the limit of x's and y's, and you can just integrate both in any format. Second one is region defined by a single closed curve, which is basically you solve the region for the limit of y's and limit of x's. So one thing is here I have used a limit function. Limit function, basically you have an equation r1, and r1 which is a function of x and y. Let's say x square plus y square is equal to a square. So if you want to put any value of y in that equation, what you can do is use limit function and specify the variable which you want to change and the value of the variable, the output accordingly. And third region is region defined by intersection of two curves. So here what you do is solve both the equations by equating them and putting y is equal to 0. That is what limit function allows you to do. All these three region I have explained in double integration one also. So fourth region is basically you have two upper and lower limits of two curves, but they are not intersecting. Instead they are defined by two given limits of x's. So that is also an easy one. You have to just integrate for the function with respect to y first and then with respect to x. So that is the code. So let's run this code. One thing here is it won't work for a symmetric function. So let's take an example here. So let us see an example. So the example here is to find surface area of the cylinder x square plus y square is equal to a square made by the plane x plus y plus z is equal to a. So here the region is x square plus y square is equal to a square, and the area you want to find is of x plus y plus z is equal to a in that region. So let us run the code here. So first thing is you enter the function of the surface integrals, that is z is equal to a minus x minus y. So instead of a I'll be using 1 because I have not defined another variable for a. So I'll enter 1 minus x minus y. Second thing is you have to define what kind of region you have. So for we have your region defined by a single closed curve, that is a circle, basically a cylinder in 3D. And then you enter the region. So region is x square plus y square minus a square, but a is 1, so x square plus y square minus 1, and then it will calculate. So the answer is root 3 pi, and the answer given in the question is root 3 pi a square, but a is 1 here, so we can conclude that the answer is correct. So next thing is why do we use surface integrals? So one of the thing to use surface integrals, like if you have a surface and if you want to find the mass of that surface, you can use surface integrals. So let us assume that m is the mass density function. Instead of z we have m is equal to g x comma y. So if we integrate the m with respect to the surface, we can find the total mass of the surface area or the surface plate. Second thing is you can find the average temperature of the surface. So let us assume that T is a temperature function of the surface plate or the surface area. So if we integrate T with respect to ds and divide the whole with respect to the total surface area, we can find the average temperature of the surface area. So that is one of the use. And one of the major uses of evaluating surface integrals is finding the flux across a surface area. So let's say here you have your vector field shown by these arrows, and this is your surface. So if you want to find the flux, that is the field cutting through that area, you can use surface integrals to evaluate that. So that is what surface integrals are used for, and thanks for watching.